Okay, so let's start. So I will continue the introduction to Python from where we stopped last time. So the next part of what we're going to look at is how you structure your code in Python. We have been touching upon it a bit, but we're going to go a bit deeper now. So as I said before, code in Python is structured by its how you format your source code. So in many cases, when you have other languages, you usually use some kind of delimiters to indicate code blocks. So for example, in C or Pascal or Java, you have curly brackets or begin end, stuff like that. But in Python, you use code indentation to denote a code block. So in this case here, I have a for loop, which loops over 5 times here. And you can see here at the end of the line here, there is a colon. And a colon at the end of the line or a statement indicates that this is a start of a code block. And if you look at the next line here, you see you have 4 spaces here. And that means that this part, the print statement here, is part of a code block and belongs to the for statement here. So in this case, the for loop will execute the print statement every time it loops around. So if we run this, you can see here that it prints out the number here, 0, 1, 2, 3, 4, and 5, or 4. And you see the print statement here, A, that is after this indented code block here. So this will not be executed by the loop because it's not indented at the same level as the loop. So that is an important kind of distinction here. That and that was also the basic idea of Python, is to have a language that has a logical layout that describes the code and forces you to kind of write your code in a way that is easy to read. So the first type of code block we're going to use is for loops. And loops is a statement for repeating a block of code several times. And there are several ways of doing loops in Python. The first one is using the for statement. And there are several versions of that as well. So if I want to repeat something 10 times, I can do like this: for I equal in range 10. That means it will loop from 0 to 9 and then print out here. So a range statement will already give you a range that starts from 0 and goes up, but not including the number here. So you can think of it, I want to repeat something 10 times. That is what you say here. You can also say that I want to start from a certain position. So for example, for range 5 and up until 10, but not including 11 then. So this should be 5 to 10. So let's see if that checks out. Yes, so 5, 6, 7, 8, 9, 10. It's also possible to specify a step. So if you want the I value here, or the variable I here, to vary with step 3, you can add a third parameter here, which is a step length. So here you see 5, 8, 11, 14, 17, 20. I can change this to 2 here. You can see here that it gives you the step length 2 instead. Many times often when you use loops, you want to iterate over some data structure. And that is something that is very easy to do without having a loop variable like you have in many other languages. So in this case here, I have a list here containing values and strings. And I can loop over each of these items in the list using also for statement. But in this case, you type for. Value is the current value in the data structure, and in which data structure I want to iterate. And every time it loops here, it will take one value from the list and assign it to this value variable here. So if I run this, it should print out every element in this list for each row. And it seems to do that. So this is a very simple way of iterating over lists. You can also do this with a loop variable. So as the first loop I showed had a loop variable I, which was the current index, which I looped over. So for example, if I have two lists I want to iterate over, I can have a loop variable I here. I can do range, and then I specify that I want to loop until the length of A. So this will have a list that goes up until, but not including the length of A. And then I use A and then square bracket here to access the elements of the lists. So now I can loop over two lists at the same time. And here I use the print statement here, first this value, comma, and then I add a string here to separate this, and then I have the second value B of I here. It is also possible to loop over lists without using, multiple lists without using a loop variable, or sorry, index variable. And then you can use something called a zip, the zip function here. So in this case, I have two lists here containing X coordinates and Y coordinates. And then I want to loop over them and get X and Y values for each iteration here. And then I just add those two together, like for zip X position, Y position, and then loop over those. And then it looks like this. And the zip here, I can do print. Just to show you what that contains. Okay. So if you look at this, the zip list is actually a iterator, so you can't print it directly. So I convert it to a list. You can see here that the zip function takes each item here from both lists and puts them together in something called a tuple, or a pair of values here. So this is something, and also this is why you can have, and then when you loop over them, X and Y are assigned the first value of this and the second value of this pair. So zip is a nice tool for enabling you to quickly extract values from multiple lists and loop over them. It's also possible, so if you have a nested list or a structure that contains a list of lists and you want to iterate over every value in those lists, you can do a nested loop. So in this case, I have 4 P in points. That means I will loop over P here will be the first item here, which is a list. Second item is a list, list, and list. And then I can loop for each list, I can do 4 coordinate in P and list, and then I loop over this item and this item, secondly. And then if I print it, it will look like this. So first it will loop over and print out 50 by 50 here, 130 and 70, 200 by 220, and 250 by 300. So this way you can loop over nested structures just by combining two loops. You can see here in the indentation also, the for loop here, colon, the code block for this loop here is this section here. So every point it will execute this code block here. Then I have the second for loop here. The code block for this loop is the print statement here. So Python forces you to kind of structure your source code in a way that it's very readable automatically. You can't, for example, if I try to just compress this here to without the spacing here, this will not work. I will get an error message here. I usually get this indentation error here if I try to do this. So indentation is very important in Python.
I have a question.
Yes.
Like the P here, does it matter it's a P or could it be any variable or?
You can choose the name. So P will be created for the loop, and you can give it any name.
Okay.
Yeah. Then there is a second loop structure that you can use, and it's called a while loop. And this is a bit different. In this case, it loops until a certain loops if a condition is true. So in this case here, I have a iteration here. I have a condition here. While this condition is true, I will execute this code block here. And if this condition is not fulfilled, it will exit the loop. So you see here that I get a lot of iterations here, but at some point here, the condition is fulfilled and it will exit the loop. So this is if you do math algorithm stuff. This is, for example, if you want to iterate until the error is less than something, and then you can use the while loop construct to do that. Another important statement is the conditional statements, to be able to kind of take decisions in your code. And the common one is the if statement, and it's also using this code block indentation. So, for example, if I want to check that a variable is 0, I use double equals to. If I equals to 0, then print this one here. So here, this code block will only be executed if this condition is true. So if I change this to 1 here, it will not execute anything here. You can combine. You can also have an else statement here. So if this is true, it executes this code block. Otherwise, it will execute this code block here. So if I change it will execute this code block here. It's also possible to have multiple if statements to check for many conditions in the same kind of if statement. So then you can have if, then in this code block here, else if this condition is true, it will execute this one here, and otherwise it's this one here, and then you continue like this. Also, it's important that you kind of keep track of your indentation here if you do if statement here. So in this case here, I have a if statement here. If it's equal, it does this code block. Then I have else here, and then you have a completely indented code block here. So this code block here will only be executed if I is not equal to 1. Then it will do both of these here. So indentation is very important if you have this more complicated if statements here. So make sure that you have the correct indentation, what you want. It's also possible to, when you are looping over things. Okay, I have a question here. How do when you should use 1 or 2 equal signs? So a single equal sign is always an assignment. If you want to assign a value to something, and you want to compare, you have a double equal sign. So that is the difference here. So double equal sign only used in conditions like in if statements or while statements for returning true. So here I have a loop here, and I want to go out of the loop at certain points, or I want perhaps to continue the loop. There are 2 statements that you can use. You can have break, and break will exit the loop. So this break statement here will go to the next code block outside of the loop here. Continue will go to the next iteration of the loop. So this way you can control the flow of the loop. You should perhaps be a bit careful about how you don't have too many of these, because it can be hard to read what happens in your loop if you have too many of these break and continues in the loop. So running this here will look something like. So in this case here, I come to, it goes to 5 here, and it says go to the next iteration. So then continue, it will not print 5 because the print statement is here. Continue is before that one, and it goes back here and goes to the next loop iteration. And the next loop iteration is 6, and it will come to number 10 here. It says print exit loop, and then it does break, and then it jumps to the position after the loop here. So just to kind of, you can try it out yourself here. So if you have the notebook up here, you can take the code here and paste it down in this section here. and just try out to find all the errors in that code and try to correct it. So execute this one here, and then you can see here you get a lot of errors here. So try it yourself and see if you can figure out all the errors in the code. And then there's also a second task here to create a loop here. I have to kind of add a, I forgot to add a code section here. So just press the add a code section here, and then you can create a loop here to loop over these items here. So I will give you 5 minutes to kind of try it out here yourself. And then I will kind of go through the answer. So you can get a bit of help if you execute the code section multiple times. So if you correct one error, then execute it again and see if you figure out the next error. Okay, so did you find all the errors? So I will start here. So the first error, it kind of, you can see here, indentation error, unexpected indent. And the reason for that is that you see that the first line here, first statement here, there are 4 spaces. Next one is 5. And Python doesn't like when you mix indentations. So the first line here should be like this. So it should be the same number of indentation or some number of spaces as the line before if it should belong to the same code block. So if we run it again, so now it says invalid syntax. And the reason for that is that the for statement is not terminated by a colon. So there is no colon to kind of start a new code block. So a for statement always has to have a colon at the end. And then we have, this seems to be correct. I have one indentation for the outer code block, one indentation for the inner code block. If we run it again, okay, now another syntax error, and this is due to the fact that print doesn't have a end parenthesis here. So we have end parenthesis like this, and now it seems to work. So you can get a lot of hints by just looking at the error messages. And my one kind of advice is to look at the first error, fix that one, run again, fix the next one, because it's easier to kind of handle, take one step at a time when you correct your code. So for the next task here, we have we should loop over the list here. So first I copy the list over here because I need to define it in my code. So like this, and then I do for, and then you can I can do for value, and then I have to specify what I want to iterate over. So then I use in, and then I say L, and then because I want to loop, I have to have a colon here to make sure that I start a new code block. And you can see the editor already suggests that I need to indent my code. So then I just print out the value of the list here like this. So this is the way you can quickly iterate over data structure. And this in operator can be used both for lists. You can have it on other data structures. This data structure must support indexed access, so to speak, or you're able to iterate in some way. So dictionary, lists, sets, there are other data structures. Numpy arrays is also something we go into in the next part of this lecture. Next, we will look at how do you, so writing Python code, you need to have some ways of collecting your code into more manageable blocks, and usually you do that using by defining functions that do certain parts of your code. And a function is created in Python by using the keyword def for define. So in this case here, I define a function here called print_doc, and after the name of the function, which is print_doc, I specify the parameters for the functions as a parameters go into the function. And in this case, I don't have any, so I just add an empty parenthesis. And then what is going into the function is added to the code block of the function. You see also that the function def here has a colon here, which means that code that belongs to the function needs to be in an indented code block like this. So if I run this, nothing happens because the code here, the only thing that happens is that Python defines this function. So now the function is available for us to call. And I can call the function just by specifying its name, a parenthesis. And in this case, I don't have any input parameters, so I leave the parenthesis empty. And then when I run this, it will execute a code block in the function like this. So you can see the output comes here, and it comes from inside the function. You can have parameters to the function, and then you just list them between the parentheses here. You can have multiple parameters, and then you can use the parameter inside a function here like this. So I define this print value, and then I can assign a variable here, and then I can pass it along to the function, and then it will. This variable a here will be assigned a value or the reference of b here, and then print it out like this. So one thing that you most you want to do is perhaps be able to modify a value that is passed to the function. And So suppose we have here a print value A, and then I want to print it out, and I want to change it to some other value of the function here. And the question is, will this work? So we just test this out here. So we create a variable B that contains the value 42, pass it along to the function print value, and then after we call this function, we print B again. And if it works like we're supposed to, it should have 84 when we call the print statement here. But it doesn't have 84. And this is something you have to think about in Python. So usually the input parameter of a function, those can't be modified. So basically those are like new variables coming in. And if you assign a new variable, no value to A here, this will be a local variable inside a function. It will not modify the value, the value referenced by the A parameter coming in. And this has to do with so A points to 42 in memory. If you do A equals 84, the A local variable here will have a reference to 84, but B outside here will still have the reference to 42. So variables coming into functions can't be modified. So we need to figure out another way of returning values from functions. And the way you usually do this in Python is by using return values. So all functions you define in Python have a return value. Even if you don't return something specifically, they will always return something, and that standard return value is none. But if you want to return something from the function, you use the return statement here. So in this case, I have defined the function f of x, colon here, and then I have a code block here. It says return sign of x. You can also return multiple values in a function. Then you just return them separated with comma signs. So how do you use this? So here I define x to be pi divided by 2. I do y equals to f of x. Then it passes x to the function and returns the calculated value on the left side here. And if I call the other one test 42 here, it will return x and x divided by 2. And then you have to have two variables that you assign at the same time when you in the return statement here. So x comma y equals to test 4, and then x will be x, y will be x divided by 2. There's many exceptions here to the rule, but for example, if you pass a list into a function, you can actually modify the list inside a function. So in this case here, I have a list A containing 1, 2, 3, and 4. I define a function modify list, which takes a parameter B, which is a list. And then if I do B 0 equals to 42, this will actually modify the list. So you see here, 42 is changed here when I call modify list. And this is due to the fact that it's a list that is passed here, and I don't change the list itself. The list, the items in the list are references which I can change inside this function here, and that will modify the values inside the list. So I will do a short 2-minute break here, and let's see if you can define the function that is described above here. So f of x should be 2x to the power 2 to x plus 3, and define it as a Python function. Okay. So what you need to do is you need to use the def function, def statement, and then we have to give the name of the function, and we have to specify the parameters here. So it should be x colon to denote the start of a code block, an indented code block, and we are automatically indented here. And then I just do return to be able to return something from the function. 2 times x plus 2 times x plus 3. And then I go out here just to kind of test that it works. I will do print like this. So that seems to be correct. So define to start define a new function, the name of the function, the parameters in the parentheses, colon to start a new code block, return to return a value here, and then I just specify the function directly here as the return value. And it seems to be able to calculate it correctly. So next, I want to look at how you structure code in a more on a higher level. So to use different, so Python has a runtime library containing a lot of different functions which are categorized into different modules. And the modules can be imported, and that means that you get access to them. And there are several ways you can do this. For example, if you want to use some math function, you can do import math like this. Then you get access to the math module, and the math module contains a lot of mathematical functions. And then you can call a function in that library called using math.sin, math.py divided by 2. And you see here it returns that value. Sometimes you don't want to you want to get the math function directly. You don't want to all the time specify math dot something. You want to get the sin function directly. Then there is another way of importing a module into your code, and that is using the from math import. And then you can specify explicitly certain functions, or you can use a star to denote that you want to have all the functions in the math module available. So in this case, if I run this, I will get all the math functions available directly to me without using the module prefix that we have upside here to specify math here. So in this case, I can use sin and pi directly here. Usually, the recommended way is using the import statement directly like this, because there is a risk when you do from, you can have a module that has the same function names, and if you import another module, it will overwrite those important functions. So that is something to think about, and then you can use instead of using the star here, you can use from math import sin and square root only. So you limit the amount of function that you import. If you use star, you get everything in that module. And the nice thing with module is that a module is not something very magical. It's something you can create very easily yourself. So if you have a Python source code, for example, with your own function definitions, you can put them in a single source code file, name it .py, and that is automatically a module. And the file name of that file is the module name. So by just putting stuff in source code files, you can use them as modules. So in this case here, I've created a module called prime.py. So this is a source text file, source code file. You can create them in Spider, you can create them in Notebook or any editor. And it contains the following code here. So this is just to make sure that I can use international characters. It imports the square root function of math. It defines a function called isPrime, which will return true or false depending on if the value passed to the function is a prime number or not. And then I return prime here. So to get this to work in our notebook, I need to download it to my notebook here, like this. So I download this prime.py file, and now I can import my file directly here using the import statement, and that will import my prime module. The import statement will actually also how to speak, it will execute any statements in the module when you do import. So import is if you have something that is not a function or executable code outside the function, it will execute that when you import. So in this case, actually, I had a print statement inside my function printing out prime here. So now we have this module available, and we can do print prime is prime here. Now you see here, it calls the function and returns true. I can check another number, and it checks false here. So this is a very simple way of structuring your code. You just put them in logical file names in the same directory as your main code, and then it's a module. In many other languages, you have to kind of, in your source code, specify that this is a module, it has a name, and you have to contains an end module and so on. So, but in Python, it's very simple to structure your code. Just divide it up in different source code files and import those in other files. Python, in many languages, you have this notion of a main program, and in Python, everything can be a main program. You can put source code, you can put statements in a source code file. If you run that file, those statements will be run. But as you saw before, when you have a module, it can, when you import, it will execute the statement in a module. And that's fine if you only have a function definition, for example. But if you have executable statements, those will also be executed if they are not function definitions. So if you want to kind of differentiate if I'm executing, if it should be a main program or a module, there is a way of actually differentiating here. So in this case, there is a special variable that's always defined for a module. It's called __name, and that will print out the name of the module which is imported. So if you import it, this name will be the name of the module. If you run it as a script, it will be specified as main. So it's so in this case here, let's see if I can download this. If I run this prime extra here, you see I did a print statement here, print name here. And when I import my prime extra here, the name will be prime extra. So this is a way of, you can check which kind of, if I'm running as a module or not. If I run this module as a, for example, if I press the play button in Spider on this module, it will not be prime extra. It will say main instead. So depending if you're importing or running your script, the name will either be the module if you import it, or main if you run the script. And this is something you will see in many Python codes. So in this case here, I have, this is my main program. This is the code that will start my program, for example, and it will import prime. It will check if name equals to main, then it will start the execution of my code. So this is, if you have seen other languages like C or Java, you often have a main routine which starts your program. And in Python, you can do the same thing using the name equals to main here. So in this case, if I run my main here, it will execute prime is prime and these two statements here. If I import this as a module, because of the if statement here, it shouldn't execute this statement, because if you import it, this will be the main name here will be prime main instead. So it shouldn't execute anything. So you don't have to focus too much on this now. You will see it later on in the examples, this if name equals to main, and it's good to know what that means. And usually if you have a name equals to main, it's in the source code, this tells you that this is the main starting point of your program code. But Python will execute anything. You don't need to have this. It will execute anything if you run the script. then we go into the next section here, and we already seen a bit about printing data out using the print statement, and sometimes when you print, it kind of looks kind of awful. It's not what you want, and then you want to kind of be able to format your data better, and that you can do using something called format strings, and that you can think about it as templates of how you want your data to look like. So in this case, I have 4 variables here: A, B, C, and D, different data types. And I have a template string here. So you see here I have empty curly brackets here. These are placeholders for where the values goes into the string. And then I call dot format here. That will transfer A into the first position, B into the second position, C into the third, and D into the fourth position here. And it will add comma and space between each value here. So this is kind of how you want your output to look. So if I run this, you see here it adds comma between those. I could also have used dashes like this. If I run this example now, you see here it formats it like this instead. So this is a way of kind of more generically defining how you want your output to look. You can also, if you want to reorder things, so the data is in certain order and you want to reorder it, you can specify numbering here. So if I specify 3, it will put 0, 1, 2, 3, 0, 1, 2. So D goes first, C goes second, B goes third, second, and first. So this is just a way of reordering it in your template. You can also order your strings, format your strings in different ways. So in this case here, I just added a less than and equal to kind of denote where the string is displayed. So the first parameter here is 15 here. That means that I want to have the output should be 15 characters wide. And then I put the string Python 3 in here. So if I run this, you will see it will add 15 characters here in the output. So you can think of it that the string will be 15 characters wide, and it will place this string on the left side here by default. And then you can also align it like you do in Excel or Word, that you can have alignment on left side or right side. You can specify here greater than sign before 15 here, and it will right align the text. So instead of having text on the left side here, you have the text on the right side. And you can have the, I don't know what it's called, this up or arrow operator here instead, and it will center the text. So in this case here, I have, it will put the Python 3 string in the middle of the field. And I can also have a field character. So instead of filling with spaces, you can fill with underscores here, for example. So you see, he puts underscores left and right. I can also change it to a star, for example. Then I get stars here instead. So it's quite flexible. I think we'll take a 10-minute break here because I have a lot of more things to do. So we get back 14:10, and then we continue from that. Okay, so let's continue. So you can also format other data types like integers and floating point values. Then you specify a special code in your curly brackets here. So in D means integers. And as with the strings, you can also control the placement of the different strings here. So in this case, I specify a 10 field width, and then I can have left, right, centered, and I can fill it with placeholder characters as well. So using these tools, you can easily create tables or values that have the same width, or every column in the table will have the same width, and the values will kind of lay out nicely that way. Floating points is somewhat more complicated. You specify colon 10.2, that means a field width of 10, 2 decimal places, and then a fixed form here, so it will be a fixed format output. Looks something like this. So in this case, I have 2 decimal places of 3.14, 4, and a total width of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a total field width of 10. Then I can have scientific notation as well. Then you have an E here, same rules, the field width of 15, 2 decimal places, and then a E for scientific notation. So then it will get this kind of output instead. It's also possible to, in your formatting, you can specify names, and then you can, in your format statement, specify names here. So X should go here, Y should go there. Makes it more easy to kind of create your template. Then you can have also provide a dictionary input to the format statement. So if you have a dictionary here, parameters like this, you can have it inside. You can provide it as the input to the formatting command. The only thing that you have to specify using double stars here in the beginning. This is kind of odd syntax here, but this is a way of providing dictionaries to the formats function. Another interesting option is every variable you create in Python are stored in a dictionary. And that dictionary you can get with access with the globals function. So the globals function will contain all the defined variables in your code or running session. So here you can see all the things we defined up until now in this session. But what you can do with this is that you can actually, instead of providing your own dictionary, you can take this star globals here, and then if you have values in your code, you can just specify those in the formatting code here. So value 1 will get the values from this variable here, value 2 from value 2, and value 3, and so on. So in this way, you can actually reference variables inside this template, this string template. Another important thing you want to do in your programs is reading and writing files. So for example, if you have a computational program, you will read your input from a file, and then when you run your code, you will write the output of your code to another file. What you do in Python is that you use the open function to create a handle or a ticket to your reference to the file on your hard drive, and then you use that variable reference for reading and writing. So in this case, it's for example, here I want to open a text file called mylefile.txt. So I do open, and then the first parameter is the file name. The second parameter is what I want to do with this file. And that is described using a text string, either W for write, read, R for read, and there is also append for adding to an existing file. So this specifies what you want to do. And when you do this, I get back, I can assign that to a variable here, which we will use to actually write to the file. So the first thing I do is I open the file, and then I can use the write statement on this object here to add things to this file. So when I do text file.write, it will add this string to the text file. I recall it again. This will also be added to the text file, and this is also added. Important thing to note here that the write statement doesn't work like the print statement. So write statement doesn't automatically terminate and go to the next line. So if you want to have a new line in your file, you need to specify the \n here. So if I execute that one, and when you are done writing to file, it's very important that you tell the operating system that we are done with this file. We don't want to kind of work with this anymore, because many operating systems like Windows, Mac, and Linux, they cache all operations to files, so it should go faster. So it's not necessarily written to disk when you executed the write statement, but when you close the file, you tell the operator, I'm done with the file, and it can continue writing down to make sure it's written to disk. So we can look at this file here. There is a special command here called cat, which you can use to display the file. And now you see here that the file contains files in all here. This is the first thing I wrote, and then I added detta skrivs ut på samma rad, this here, and then denna text kommer på en ny rad. I don't know why I have this text in the middle here. I'm just going to, it's, sorry for that. So this is what the file contains. Reading, when you use the W attribute here when you want to write, it will create the file regardless. If there is an existing file, it will be overwritten. If there is no file, it will be created. So the only difference is when you read files, it has to exist.
Okay.
Yeah, but when you create them for writing, it will create the file automatically.
Okay, great. Thanks.
Yeah. And then reading from a file is very similar to writing to a file. The only difference is that you specify the R in the second parameter of the open statement. You get back an object again, which you can use for reading. And then you can there are multiple ways of reading the file. So you can do text file.read. That will read the entire contents of the text file and place it in a string variable content. And then you do text file close again, just like we did before. So now I will open this file here and I will read it. And you see here I got the content variable now contains the entire contents of my file. This could be, if you have, for example, in many large finite element applications, for example, you have output files that are gigabyte of size, and it's not a good idea to read the entire file into a string variable that is 1 gigabyte. So usually this works well for smaller files, but for larger files, you need to kind of read it in a more sensible way. For example, line by line or something like that. So in this case, I open the file again. What I can do then is there is a method called readLine, which will read one line and return that to a string variable. And then I can loop until the line here is empty. If the line returned from readLine is empty, then we are at the end of the file. And then I close the file again. So in this case here, you can see here I print out each line which I read in. But you see here that there's a strange extra line here between. And that is because readLine will also read the line return. So when I print it out, it will print out with a line return. So the print statement will print the line, it will add a character return, and then print will also add a character return. So that's why you get the double line here between. You can, of course, if you don't want this, you can actually use the strip function that we had before. So in this case, I can right strip my string, which will remove any trailing things at the end of the string. For example, a character return. So if I run this again, it will not print out the character return. So this is a way of kind of cleaning up the things you're reading in. You can also actually use the for statement to read a file. So in this case here, I can do for line in a text file, and then I can just print them out. So this is a really nice way of doing it. For line in text file. It's like you can read the code and understand what it does. Another way of reading is actually, if you want it in a list, so every line in the list, you can use the read lines function. That will actually read each line and put every line as a row in the list or item in the list. So if you run this here, you can see here the lines here will actually contain the first line here, including the character return, and then the second item in the list is the next row here. Another nice thing which could be good to do with files is that you can use the with statement to open files. And the nice thing with the with statement is it guarantees that the file will be closed. So in this case, instead of just open the file and assigning an object to this file, you can do with open myfile.read as text file. And then I read all the stuff I want to do. And then I don't have to do anymore, because everything after this code block has been executed, the text file object will be closed automatically. So this is a way of ensuring that you always close the file, and you don't have to worry about cleaning up afterwards or forgetting to call close. Error handling is also something you have to think about. So I usually try to kind of code defensively, not kind of checking if certain conditions are true before executing. So one way of doing that is actually to call functions to check, for example, does the file name exist before I open a file for reading, for example. So in this case, there is a module called OS, which stands for Operating System Functions, and it has some versions of, for example, OS path exists. Will check that the file name actually exists on your hard drive, and if that is true, it will open the file. Otherwise, it says that it's not found. So this is one way of doing it. So calling functions to make sure that all the prerequisites are met before you execute a certain command or open files. But there's another way of doing that in Python. So, for example, if you try to open a file that doesn't exist, we can see what happens here. So this my file does not exist. You get this kind of output here. So file not found error, no such file or directory. And all this block here is something called an exception. So when something goes wrong, Python will stop and throw something called an exception. And if you don't handle those exceptions, you will get this kind of error. But you can actually catch this error message and handle that. So for example, that is done using the try. So try is a special code block that will execute this code block, and if there is an exception, it will execute the code block here after the except here. So if this doesn't work, it will just print out the file couldn't be opened. So instead of getting this ugly message here, you will get something like this. The problem with this code here is that it will catch every exception that Python can throw at you. So it could be that the file, there is some permission errors or something, other error that occurs, but you will never find out. This code will always print out the file couldn't be opened. So what you can do to kind of make sure that you only handle those exceptions that you want to handle is that you specify which exception you want to handle. So in this case here, I can specify here, except file not found error. And then I print it. Then it will only catch that error exception, and other exceptions will kind of stop the code and be handled a different way. So in this case here, this will still work. Then you can also handle different error in different ways. So you can have file not found error, you can have permission error, for example, and you can just list all those exceptions, and you can handle those errors differently depending on which exception that has been thrown. So in this case, it's difficult to kind of try this permission error here, but there is an exception called permission error that if you don't have the permissions to open a file, it will throw that permission error exception instead. There's also possibilities to get information from exceptions as well. So in this case here, I can do accept file not found error as E, and then I can actually query the exception, which file wasn't found. So instead of printing out myself, I can actually query the exception for the actual file name that was not found. So file on my file.txt couldn't be opened. And finally, there is also one problem with exception handling is that it breaks the program directly, and sometimes it doesn't clean up after itself. So if you want to make sure that, for example, files are closed even if you have an exception, there is another clause you can add to your try section. It's called finally. So if you get some error here inside your code, it will always call the final section here to make sure that both the input files and the output files are closed. You see I have an error here, and then it will always call the stäng öppna filer here. So this is where I always call it. So I will now continue to the next lecture, which is Introduction to Numpy. And you can find this in the courses. So Introduction to Numpy here. If you click that link, you will get the next lecture here. So if you want to follow along, you can. I'll give you a minute to open it. So it's Introduction to Python here in the Canvas section. So as this course is about creating a computational code, we need tools for doing the computations. And as I told you in my first lecture, Python is an interpreted language. It executes the code line by line. C++ and Fortran and other language, they compile the code to machine code, and the application itself is machine code when you have compiled it. So it's very fast. Python translates every line to machine code step at a time. So executing fast loops is kind of very hard to do very efficiently. Also, the data structure that are built into Python, like the lists and dictionaries, those are efficient for handling lists and dictionaries of kind of mixed data types. When it comes to numerical computing, you usually only work on numbers, floating point, integer numbers, and so on. And you need something that is really efficient, because you can have really large matrices that you want to do computations on, and you can't use lists and dictionaries to create matrix-like data structure, because it would be extremely slow. And many scientists realized that early on, that there was need for something more efficient in Python. And what they came up with was first it was called numeric, and then it was called numeray, and then finally it was called NumPy. And NumPy is an extension module implemented in C with very high performance machine code to handle large arrays of the same data types. So in this case, could be vectors, matrices, and so on. But they're highly efficient for doing just that. But they can only handle one data type per object or variable. So you can't mix and match like strings, floating points, like you can do in list. But it's very efficient for handling large arrays of single data type. NumPy comes built into Anaconda, so you don't have to do anything. It's part of that. And if you want to compare it to something, it's similar to the matrices that you can do in MATLAB. So it has a lot of the same features that you have in MATLAB. You import NumPy the convention is using this here. So import numpy as MP, and that will have the effect that every numpy function or data type has to be prefixed with MP. And that is actually a good thing, because many of the functions in NumPy actually overlap with many of the math functions in Python. So it's a good way to prevent you from calling the wrong function. So we execute that one. So we have imported NumPy now. The main data type in NumPy is the array object, and that is and you use a special function called array, or you use different. There are multiple functions for creating these object types. So if you want to create an array, you do like this. So a equals to mp.array, and then you specify the values you want to go into the array and the data type. So here you need to specify the data type, and you don't have to specify actually, because we'll figure it out. So the array will get the data type either by specifying it kind of guesses the data type what you specify here in the input, or you explicitly specify it like this. So in this case here, you see, as I specify that it should be a float, you can see when you print it out here, it will print a floating point vector here. If I would leave this out, I have the examples here. If I leave it out here, you see here, it will try to figure out the data type from the input here. So if I run this here, you can see it will be an integer vector instead. And also here, if I do floating point values to the input for this array, it will create a floating point array. NumPy supports arrays of multiple dimensions. Basically, there is no limitation in the number of dimensions. So for example, if I want to do a two-dimensional array, I just specify like a nested list here inside. So I have a list here, 1.2, 3.4. So this is the first row, this is the second row. Same thing here, I can have this is a 4-column array with 2 rows. So you can see here that it looks like this. And it will print them out kind of with the correct structures. So one thing it's important kind of to know is that how computers store things in memory. So when you allocate an array, even if it's 2-dimensional or 3-dimensional, every value is stored in a single continuous block of memory sequentially. So there is no, the computer doesn't have a notion of 2-dimensional memory. So memory is always stored like in a sequence. And NumPy stores the arrays in kind of a C++ convention. That means that it stores row-wise. And what does that mean? So if I have an array like this, 2-dimensional like this, it stores them in memory row. So first it goes this one, and then it goes to the next row, next row, next row, next row. And in memory, it looks something like this. So it's just stored in a sequence of numbers in memory. There are Fortran, which is also a computational language, stores data column by column. That means that it's stored in this direction instead. NumPy can handle that as well, but by default it uses the C notation, row-wise. And this kind of storing as a sequence in memory, that also means that you can actually reinterpret the way the data is, how you interpret the data in memory. So you can do reshape of an array without reallocating. You just kind of, this is a 4x2, now it's a 2x4. The number of elements is the same, but you interpret it in a different way. So you cannot actually query these array objects you create are kind of intelligent objects. They have a lot of attributes that you can query. There are methods you can call to kind of see the shapes of them and so on. So in this example here, I create three variables A, B, and C with different rows and columns. and data types here. And the first attribute we look at is the shape. And shape describes the actual layout of your array in memory. So in this case, the first one, A here, is it has 4. It's a single vector, so it has only 1 dimensions of 4. And this one, the B, is a 2 by 2 array. And this one here is actually a 2 by 2 by 4, so it's a multi-dimensional array. And the shape kind of gives you the dimensions of the array. One nice thing, if you want to kind of query an array and assign variables to, for example, the number of rows and columns, you can do it in this way here. So row comma C equals to B dot shape, and then R will be the rows of the B array. C will be the columns of the array. So it's one way to kind of assign variables directly to the number of dimensions of your array. Also, the number of rows and columns for the array. The dimensions here you get using the ndim property. So here it is a 2-dimensional array, and I get the 2 here. There are several other data types or attributes you can query. So shape, ndim. You can also query the data type, the number of elements in the array using b.size. So that is the total number of values in the array. Item size will also give you the number of bytes that each element takes up. So for example, if we run this here, now it's an integer array. You can see here that this is a 64-bit integer. That means that every integer takes up 64 bits in memory. There are a total of 4 values in the array, so 1, 2, 3, and 4. And every item in the array takes up 8 bytes. 8 by 8 is 64. So it's an 8-byte integer. So this is where so if you have specified, for example, floating point values here, it would have been a bit different. So now it converts to 64 bit floating point value. That is, the floating point consists of 8 bytes. So now you see here you have 8 bytes here for storing each floating point value. Takes 8 bytes in the array. Okay, so let's see here. As I said before, you can change the shape of an array. Numpy is very clever in its design, so it tries to avoid reallocating memory as far as possible. Because reallocating memory, especially if you have a large array that is several millions of elements, you don't want to reallocate when you change the shapes of the array. Just to kind of illustrate this, you don't have to kind of, this function here I defined will return the memory address of the actual array. So in this case, I create a variable here. I print A, and I print the memory of A, and then I do A flat here. I will do a reshape here. This is the special function that will change the shape of the array without changing the. It will preserve the data inside the array. And let's see here what happens here. So if I run this, so first I have an array that is 2 by 2, and you can see here that you have a long address here, 5152, and then I reshape it to be 4 columns and 4 rows and 1 column, and you see the memory is the same. So it tries to avoid reallocating and creating new space. So it just reinterprets. So A flat is just an interpretation of A, but using 4 rows and 1 column instead. One thing to note, though, is that if you change A flat will also be changed. So you can see here, I changed row column, row 1, column 1. And you can also see here that we indexing in NumPy is 0-based. MATLAB is 1-based. So the first row in an array is always 0 in NumPy, 1 in MATLAB. But you see here that the first element here is 42, and also in the A flat. So both A and A flat points to the same memory values. So if you don't want that behavior, you do like we do with list. You use the copy command or copy method to make sure that you create a copy of A. And then you see here that those two are actually two different memory locations now. So NumPy tries to make great length to make sure that it doesn't reallocate anything. So here I have a two row, 4 columns array. I reshape it to be flat, and I go back and change it to 4 by 2. So here I go from 2 by 4 to 1 by 8, and then 4 by 2. Note that this is not the same thing as doing a matrix transpose. A matrix transpose, there is a special method for that does the mathematical transpose of a matrix. So you can see here, this one here is not the same as this one here. So that was reshape. So reshape tries to change the shape without changing the contents of your array. It just kind of reinterprets. So the criteria is that you need to have the same number of elements in your array. Otherwise, it doesn't work. If you want to change the number of the size or the number of items, or if your matrix grows larger, you can use the resize function. So I create a 2 by 2 here, and I can do NumPy resize, and then say it's 9 by 9, and it tries to copy over the data from the previous array as well. So if you run this example here, so you see here, I had the data inside arrays 1, 2, 3, 4, and now it's kind of just fills out this 9 by 9 matrix with the same data. You also have 4 by 4. It tries to preserve the data that's already there in some way. Sometimes, or most often, you need to kind of create arrays that are larger than you can do using an array command. You want to kind of, usually many arrays you create are either 0 or 1 and from the beginning, and you want to create those in an efficient way as well. So there is it's very similar to the zeros command in MATLAB. So you do a equals to num plus 0, and then you specify the dimensions of your array like this. And you can also do with floating points. So here you can specify, if you don't specify anything, you get a floating point, and you specify the data type here, you get integers here. And there is a similar function called ones, which creates an arrays filled with ones. And ones is very good if you want to fill a matrix or array with the same number everywhere. You can just create an mp.ones and just multiply it with 42, or the value you want to change it to. But the interesting thing is that all the normal operations that you do, multiplication, addition, will work on all elements at the same time. So when you multiply an array with a scalar value like this, all values in the arrays will be multiplied with that scalar value. So you see here now every value in my array is 42. You can create ranges in normal Python, what you do with the loops. There is a command called arange here, which creates a range of values from 0 to the value you want to specify. So this creates a range from 0 to 9, and it's an integer by default. You can of course specify, for example, float here as well, and it will create a. No, I think you can specify e type. Then you have floating point values here instead. So you can use by default it's integers. And combining arange with reshape, you can quickly create certain kind of arrays filled with values ranging from 0 to the number of elements in the array. So in this case, I do a range from 0 to 99. I do a reshape here to an array by 10 by 10. This is not costly operation because it's just a reinterpretation of a single vector into a two-dimensional array. So now you see I get an array that is 10 by 10 with values from 0 to 99. You can also, like you can do with the range function in Python, you can do the starting value and the end value. You can also have a step here. Yeah, as I said, you can specify the data type here using the D-type float here afterwards. You need to specify D-type here because you have some other parameters that goes in before here. So if you just specify float after the first one, it interprets this as the second argument here, which is conflict. So you need to specify this, the name of the variable you want to specify here. It's also possible to create identity arrays, that is arrays that have the 1 on the diagonal and zeros otherwise. So this will be, so you have ones here in the middle. You can also specify a second parameter here will give you, I think it will, no, I was wrong. It was probably, let's see. I was wrong. Yes, so that's, you get the diagonal here. The arange method is good to kind of, if you want to specify ranges that's integer ranges, for example. But if you want to specify, for example, an interpolation, the range, for if you want to plot your numbers, for example, there is a function called linspace instead that gives you, you give the starting point, starting value, end value in floating point, and those values are guaranteed to be part of the array that you create. And then you specify the number of values you want to have in that array. So in this case here, I go from 0 to 1, and you can see here that 0 is part of the array, and also 1 is part of the array here. And the same thing, if I do 20, I get 20 values, and 0 and 1 is part of this. So this is very good if you want to create X ranges for use with plotting later on. So it's similar to the colon notation you can do in MATLAB. You put 0, colon, step, and end value. So this is just, it's very similar to that. As I said before, you can, all the operations you can do with plus, minus, multiplication, you can do with element-wise on the arrays. So here I have an array looking like this. I can add a number, scalar value to the A, and it will add the value to all elements in this. And this is a very fast operation. So this is done implemented in C. So it's much faster than looping over an array and changing the values. Same thing with multiplication. You can also call the built-in math functions in NumPy. So in this case, NumPy has all the built-in Python functions for math in versions that can handle arrays as inputs. So if you do mp.sin_a, it will calculate sinus for every value in the array A, like this. You can negate an array by using the minus sign in front of it. You can add two arrays together. And also the array sizes doesn't have to be the same. So arrays are not mathematically defined as matrices or in that sense. So if you do, for example, here I have two arrays here, 1, 2, 3, and I have a 5 by 3 array like this. Then if I add them together, it will kind of just continue adding this array to the another one here. So you can do plus and minus on arrays that do not have the same size. As arrays are not matrices, you need to kind of specify another operator for doing matrix multiplication. So there are several ways of doing that. So in this case, I define a 4 by 4 matrix, 4 by 4 array. You can do it either by calling the dot function here, a dot a, that will be a matrix multiplication, or the at operator, which has been defined as matrix multiplication by NumPy. If you do the normal multiplication operator, you will get an element-wise multiplication. So there is difference here between matrix multiplication and element-wise multiplication. By default, the normal star operator for multiplication is element-wise multiplication. As with MATLAB, you can access individual elements. As I said, it's zero-based, so row 1 is 0, column 1 is 0. And you use the same kind of notation as with list almost. So here I get, so this is a vector of 25 elements, and you get A2 is the third element, and use the brackets here to get access to that element. And if you want to access an element in a two-dimensional array, you use brackets and then the row, comma, column here. So it's not the same syntax as for lists. I don't think you can use the same. You could use, you can use both notations here. So this is 1 by 2. So this is the 7 elements. So you can actually use the same list. This will also work. E1, 2. So it's the same thing. So you can assign values in the same way. So you can do A.A2 equals to 42. You can do specify the rows and columns and assign a value like this, and that will also work. You can index just like we did with lists. So you can specify start and end. So that will access values between start and end -1. You can do start colon, and that's values start to the end. And then you can do colon end values to n -1, all values like this. So this will extract A1 to 5. So that is starting from 1 here to 1, 2, 3. This is the 4 here, but not including this one here. So the last index will never be included. This is a specific thing for Python that you have to think about that. Another thing that you have to that is also important when you do this kind of slicing, Python tries to create a new array object that looks at a certain part of the larger array. So it tries to avoid doing reallocation in these cases as well. So if we create an array, a vector of 25, and we do a print A here and memory of A and the data here, and we access A, assign B to a certain slice of A, you will see here that the memory here will be the same. So this is the data allocated memory in the computer's memory. And the first one, a memory of A, that will be a kind of offset of the other one. So it's part of the same allocated memory, but just a different view of that memory. So even here, it's very efficient to do this kind of operations. It's not very costly to do this slicing. And here are some other examples here of doing slicing here. You can use the same notation here, like we do with the list, that if you do -1, it will wrap around. So this will be except for the last one here, and except for the last two one. And this is the last element of A. And here you have elements 4 to 9 with a step of 2. And here is also, you can do reverse order here of an array as well. So this will reverse the order here. And you can do that in 2 dimensions as well. And here are some other options here that you have all rows in column 0, all rows in column 1. So this is very similar what you can do in MATLAB as well. It's also possible to mix array and list notation. So if you assign, for example, row 1 a list, the array will automatically convert the list and assign those elements in the array. So you can kind of mix and match both arrays and lists. You can even loop over an array in the same way you loop over a list. There is no kind of Python will know how to handle that as well automatically. So this part here, that is actually a normal Python list. So you don't have to create an array to assign a row in a array object. You can just assign the values like a list like this. There are some methods that are part of the array object that can be useful. For example, if you want to sum an array, you can use the a.sum. That will calculate the sum of all the elements in the array. You can sum only columns. You can sum only rows as well, using specifying an additional parameter here for the sum function. And then it sums other rows to columns. And you have the same thing with the product. You have a product method here to calculate the total product of the array. And you can calculate the product of the columns, product of the rows as well. Then there is also, what we talked about now is array objects. But there is a specialization of the array object called a matrix. And the difference with the matrix and the array is actually not that big. So a matrix is an array, but it knows about linear algebra. So it has built-in linear algebra operations. So here I create, but instead of creating array, I use the matrix function to create a matrix. And what I can do then is I can use the a.t here for doing a transpose of the matrix. I can use the normal multiplication operator for doing matrix multiplication. I can also call the a.i for getting the matrix inverse. And this can be quite useful if you want to create matrix expression, linear algebra expressions in your code. Then it could be useful to have the matrix data type instead of using the array, because an array is just a generic multidimensional data structure. But the matrix is actually something, it's a two-dimensional matrix vector which you can use to kind of calculate linear algebra with. So I will shortly go through. So what you can also do, which is similar to what you can do in MATLAB, you can save your arrays to disk very easily. So here I have two arrays, and I can save them using the save command. And I just specify a file name and the actual array, and it will save those to disk. And you can see here, I created two files here on my disk, and I can look inside them. And you see these are stored, these are binary files, so they are stored with the bytes that for each, so it's very compact storage. And you can read them back using the load command. Just to show that I get actually the data back here, I plotted them as well. You can use, if you want to store multiple in a single file, you can open your file yourself as a binary and then just the save and specify, instead of file name, use the file object here. You can also read and write text files. So I downloaded a file here called ubw.dat, and that will it can handle text files. And so this is a file consisting of this here, and it will read data structured like this with spaces in between. And here you can specify, for example, load text, and then I say that the first two rows, ignore those because those are not numerical data. And it will try to interpret this other part as an array. So the normal way of doing this without this load text is to do your own looping, to loop around and convert your data into an array yourself. You can also use the save text here to dump an array to disk, using the same kind of similar format. You can see here that you get the data just with spaces in between. I think I skipped this here now. I will go just finally before we end here today. So if you want to solve an equation system, there is a special module that's called linalg, which you can use to which contains some solution functions here. So here I have a and b, and x equals the solve here, and it will solve the equation system. So this is the solver that you can use if you want to solve a linear equation system. So I think this will be all. And I think this is final lecture. Then we have an Easter break. I will put this lecture as well to on YouTube, so you can look at it.